Hey everyone, we're going to be going through a 7.2 problem real fast, the car banking problem. So if you didn't know you can do this, this is kind of cool. You can make it so that a car turns without the person ever having to turn the steering wheel. You could make it so that a car turns even if it was on ice. All you have to do is you bank the turn. If the car is going the right speed, the car will turn exactly the way you want it to, even without that person having to steer. This is a major part of roadway design, of highway design. It's something that's used in airplanes. It's something that's it's used all over the place. So it's kind of fun and kind of interesting. So we're just going to do a quick little problem that explores the concept. Yeah. So let's go ahead and take a moment. So let's assume that we have a car that's moving 27 meters per second, which is 60 miles per hour, which is, let's be honest, probably a lot slower than a lot of you guys drive on the roadways. And it's taking a turn that is banked at a total of 10 degrees. We'll say the mass of the car is 950. That's probably about a normal mass for a regular car. Larger car will be heavier, smaller car will be lighter. What is the radius of the turn that the car would make with no frictional force? So these are the things I'm going to want to see. An overhead diagram, a head-on sketch of the car and the turn, a free body diagram, and then the use of our central force model. There are two bonus questions down here. I'm not going to go through them in this video, but if you want to think about them, they're both kind of interesting. So let's go through and start working on this. So first thing we need is an overhead diagram. So a car is going to be making a turn. I will go ahead and say that this is the turn that the car is making. I don't think that the car, that the turn has to be a complete circle. The turn could just be part of a circle, right? So we'll go ahead and say that this right here is our turn. You can imagine like your car, right? So you're a car driving along here. So this is you, and you kind of follow this path right here. This section from here to here is a circle. So it's not all of a circle. So let's see if I can actually get that to the center. Center of that circle is about here. So the question is if you're moving at these 27 meters per second along this circular path here, what radius could we get, assuming that the path is banked 10 degrees? It does have to be banked towards the inside. I'm hoping that was somewhat obvious from the picture, but let's go ahead then and look at this. So if we look at the roadway here, and here is our car. And then here's, one of you guys. Ooh. Hands on the steering wheel. All right, whatever. So this is you and your car, 10-degree bank. And the question is how big of a radius could we do here? If you're going at just the right speed, actually, you don't need to use the steering wheel, but we'll get there. All right, so that's the overhead view. I don't really care how much of the circle you made this. This will work even if you're going in a complete circle or if you're just going in a small circle. This banking will put you on some sort of circular path at the right speed. If we're going 27 meters per second, let's go ahead and draw out a free body diagram. So there's only two forces acting on this car. There is the force of gravity on the car by the Earth, and there is a normal force. Now, the normal force is not straight up. The normal force is banked by 10 degrees. That's what the banking does, which means that we can actually split this into two parts. There is the upwards part of the normal force, and then there is the part of a normal force pointing to the left. Now, the upwards part of the normal force here, on the car, by the road, the upwards part of the normal force here is only going to go into balancing out the force of gravity. But the leftwards part of this normal force Well, that's going to be our central force. So we have an upwards part of the normal force acting. Let's change the color. We have an upwards part of the normal force acting on this car, and then we also have a leftwards, or in this case, well, rightwards if you're the driver, force acting on this car that is causing it to make this turn. So this will be our central force. We need to figure out how big this force is so that we can plug it into our central force model. All right, well, if we know that the force of gravity is balanced out by part of this normal force, let's start by calculating that. We know that the force of gravity is always equal to the mass, which was 950 kilograms, where we know that the Earth will pull down for 10 newtons for every kilogram. So that's a total of 9,500 kilograms. Well, if that's 9,500 kilograms, sorry, newtons, my bad. So if that's 9,500 newtons, that means this must also be 9,500 newtons. Now that is not the entire normal force, though. That is only the vertical portion of it. We now need to get the horizontal portion. So the way I'm going to go about this is, if we know that this 9,500 is the vertical portion, I'm going to find the entire normal force, and then I'm going to use that to find the leftward force. Sorry, I'm getting messages and it's distracting me. All right. So we know that the total normal force, whatever it is, times, this is the part that's the cosine of the angle, right? Times the cosine of 10 will be equal to 9,500. So the cosine portion of that triangle is equal to the total normal force times that cosine of 10, which means that total normal force will just be equal to the 9,500 newtons divided by that cosine of 10. So, calculator that you can't see. I really did for a while try to make it so that you guys could see my calculator, but it just became way not worth the trouble. I mean, I hope that you guys know how to calculate that. I get a total of 9,647 newtons. So the entire normal force is a little bit higher than just the vertical part. That makes sense. So the roadway is actually pushing on the car a little bit more than gravity is pulling it down. But that makes sense, because the roadway is not just holding the car up. Now the roadway is going to hold the car up and turn the car. All right, so let's figure out what's this horizontal portion here. Well, if the cosine of 10 is 95, if the cosine of 10 is the vertical portion, the horizontal portion must be the sine of 10. So 9,647 newtons times the sine of 10. I get 1675. Oops. All right, now we could go ahead and just run this through on our Pythagorean theorem, just make sure real fast. If I take the 1675 squared, and then I take the 9,500 squared, add those two together, and then take the square root, I get the 9,647. Good. So just making sure that those two added up, checking out the Pythagorean theorem. So let's go back now to our free body diagram here. So that means that our car is being pushed upwards 9,500. We don't really care about that because that start part's being balanced. But this 1675 is to the left. That part is unbalanced. That is the part of that force that will be accelerating our car. So we have an acceleration inwards from a 1675 Newton force acting on that car. All right, so let's go through and do the math. Let's split this up. So we did an overhead diagram. That was number 1. We did a head-on sketch of the car. That's number 2. we did a free body diagram, number 3. And then number 4, our central force model. So we know for something going in a turn, the amount of force you need to go in that turn will be equal to the mass of the object times the radius of the turn, times the velocity at which you take the turn divided by the radius of the turn. So I'm just going to go ahead and start plugging things in. The amount of force we're using is 1,675 newtons. We know that the mass of the car is 950 kilograms. We know that this car is going 27 meters per second. And what we're trying to find is the radius. So what I'm going to do is I'm going to take this 1675 and swap it with the radius. So just go ahead and swap them. So I get 950 kilograms times 27 meters per second divided by 1675 newtons. Sorry, that I can imagine that's probably difficult to read. Let me move that away a little bit. I got to make sound effects when I do this. It's a ritual. So we'll move that over here. So we know that we can solve for our radius by calculating that out. And again, when I throw that in my calculator, I end up getting 41.34 meters. So I'm going to round that down to 41 meters. So what this means is, so 41 meters. So this means that if our car is taking a turn with a 10% bank, that our car is going the speed we said, about 60 miles per hour, 27 meters per second, that using no friction, meaning the road could be made of ice, it doesn't matter. We're not wearing the tires laterally at all, although I guess whatever. But there's no friction acting on the car at this point. Then we know that we can get a total of, we can do a 41 meter turn here. I'm not going to go through either of the bonus questions. They are, they are trickier. But that said, they're definitely doable. But this is a good spot to start with. So 41 meter turn will happen there. All right. I'll probably add a second page for work for the bonus questions if you want to see how I do that. I'm just not going to go through it in the video right now. So quick review of everything we did here. First, we drew out the path. I did it overhead and I made it so I could clearly recognize the circle that I was taking. I wrote my information here. Second, we had the head-on picture here where we can see the person driving. We can see how the road is banked, and I use that to help me set up the free body diagram here. The free body diagram is one that we've done many times before. Oh, by the way, it would not have been in a, well, you might be tempted to split the force of gravity here. The issue with splitting the force of gravity here is, yeah, don't do it. I can see how that throw people off. So if you end up splitting the force of gravity here because it is a sloped ground, I can see how that's probably not full. Tell you what, I'll put a little note on the problem when I actually assign it to don't split the force of gravity here. And then finally, once we figured out how much unbalanced force we had, the 1675, we figured out how big of a turn that we could go ahead and make the car go through with that 1675. All right, everyone. Let me know if you have any questions. I'll gladly work through another one of these with you anytime you want. Some of you are already showing me positive stuff here, and that's great. And again, we're looking towards the last two targets of the entire year being presented next week. So at that point, you just have until the end of the year to get as far as you can to show me as much stuff as you possibly can. Some of you might be totally done with my physics class in 2 weeks. Kind of cool, right? I mean, I miss you, but easier for you. All right, everyone. Let me know if you need anything. Have a nice day.